Okay, so now that we've seen how to represent chemical reactions and chemical equations, we've done all sorts of things with chemical equations. We are now going to take a look at examples where we actually do encounter chemical reactions in sort of an everyday setting. And what we're going to take a look at now are chemical reactions that occur in aqueous solutions. And this whole chapter is going to be looking and focusing at aqueous solutions and reactions that occur in this particular environment. All right, so we can say, let's put some abbreviations. We can say chemical reactions, so reactions rxns in aqueous, AQ, in solutions, I'm going to abbreviate it SOL and S. Okay, so these are, draw some arrows, that's chemical reactions in aqueous, and then that way. So I'm going to use those abbreviations from this point onwards. So when we talk about a solution, first of all, what a solution is nothing more than a term we've seen before, which is a homogeneous mixture. And the homogeneous mixture is composed of multiple pure substances that are not chemically combined, but they share the same physical space. And in a homogeneous mixture, the mixture looks the same throughout. Okay, so you can't tell one part of the mixture from the other part of the mixture. A solution is just another term for a homogeneous mixture. Now, solutions generally are made up of two components. It's made up of something called a solute and something called a solvent. And the difference between them is just the relative amount. So the solute is a thing present in smaller amounts. And then the solvent would be the thing present in greater amounts. Okay, the solutes, we can actually have multiple solutes in a solution. But there's only one solvent, right? There's only one thing that's present in greatest amount in a solution. Something that dissolves in a particular solvent is said, the term that we use is said to be soluble in that solvent, right? So as a simple example, we'll take a look at one example here in a second. When we talk about solutions in our class, by default, what we're going to be referring to are aqueous solutions. And in an aqueous solution, what this typically means is that water is the solvent. And water is a good solvent. It's sometimes referred to as a universal solvent because it tends to dissolve most things, not everything, but it tends to dissolve most things, meaning that most other things are soluble in water, is why it's sometimes called a universal solvent. So when we are dealing with a solution where water is the solvent, we refer to that as an aqueous solution. And if you remember, we use the abbreviation AQ as our state symbol to show that that particular thing was aqueous. It was dissolved in water. So as a very simple example, if I have a container and I have some water in it, some H2O, and I added a pinch of salt. Okay, so a pinch of NaCl. Okay, what I've just made in here is I've made now a salt water solution. So the solution itself has a couple components. So the solute here, the thing present in smaller amount, is the salt, sodium chloride. Obviously, the solvent is the H2O, it's the water, and together they make our salt water solution, right? And we've encountered solutions similar to this in the past. We're going to see examples of lots of these here as we go through this section. So when a solution forms, that solution itself is going to have a characteristic known as an electrolytic characteristic. And we can define, first of all, an electrolyte as something, when dissolved in water, is able to conduct an electric current. Okay, so that's what we define an electrolyte as being. You probably have seen or heard the term electrolyte before, for example, in reference to energy drinks or Gatorade or stuff like that. You replenish lost electrolytes. Well, what exactly is an electrolyte? So an electrolyte is something, so the example that we have here is sodium chloride, which is regular table salt, starts off as a solid. If we add that to some water, what happens is we end up forming these ions that make up sodium chloride. The ions here are sodium, Na+, which is now going to be dissolved in water, so it's H2. And then we're also going to get the chloride ion, Cl-, also dissolved in water, which is also going to be AQ. The fact that these ions form allow this to conduct electricity, and we refer to that as an electrolyte. So ions form through dissociation. Yeah, and dissociation is just a splitting apart of an ionic compound into its ions. Yeah, and the fact that we have these ions present then allows this to conduct electricity. This then can make it an electrolyte. So in other words, in order for something to be an electrolyte, we need to have ions present, something that is able, or things that are able to conduct an electric current. If we had a saltwater solution, shown here, for example, we stuck a couple of electrodes in here. These are electrodes that are coming down, connected to a power source. Those ions that are in the solution are able to complete the circuit, allow the current to be transferred, and as a result, our bulb here is going to glow. So a very simple experiment can be performed to judge or to determine the electrolytic nature of a substance. So dissociation happens when ionic compounds break apart into ions, makes them electrolyte. What can also happen is ionization can occur where a molecular compound forms ions. And these molecular compounds, that's another term for your covalent compounds. And sometimes these are able to form ions in solution. That process is called ionization rather than dissociation. So we have electrolytes that form ions in solution. They conduct electricity. We also have non-electrolytes. As you can imagine, a non-electrolyte does dissolve in water, but it does not conduct an electric current. And what this means then, by contrast, is that even though it dissolves, whatever the substance is, no ions are produced. Instead, for a non-electrolyte, how does this dissolve? It actually dissolves not as ions, but it dissolves as individual molecules. Instead of ions. And because there aren't any charged species, so no charged particles present, that means it's unable to conduct an electric current. So an example of this would be very similar to the one we looked at before. If I have a container of some water in it, and now instead of adding a pinch of salt, I add a pinch of table sugar, okay, which is sucrose. Okay, if I add the sugar to here and I stir it up, okay, it does look like the sugar dissolves, it's soluble in the water, but does it actually form ions? And the answer is no. So if I have my sucrose over here, which is a solid, it's a crystal, it's way more complicated in makeup than table salt. If I add it to some water and I stir it up, okay, this doesn't break apart into ions, it actually breaks apart into individual sugar molecules. Okay, so these here are sugar molecules that are now dissolved in water. And these sugar molecules are neutral. So they remain intact upon dissolving, they don't split into ions, and as a result, no ions present in here. So the bulb then stays unlit, doesn't conduct electricity, so we call it a non-electrolyte. So under the umbrella of electrolytes versus non-electrolytes, we have two categories. We have strong electrolytes and we have weak electrolytes. A strong electrolyte is one that dissociates completely in aqueous solution. And what that means then, if something is able to break apart completely into ions, what that means is that we have lots of ions in solution. And if there are lots of ions, this is able to conduct electricity very well. So we call it a strong electrolyte. So strong electrolytes would include things like your ionic compounds that are soluble in water. So if I add again my sodium chloride to some water, okay, the sodium chloride is going to break apart, it's going to dissociate completely. So all I have at the end are just ions. So only ions in solution. None of the undissociated compound remains. Okay, all you have are a bunch of positive or negative charges. So the bulb here is going to glow very brightly as a result. Other strong electrolytes include things like strong acids. Okay, so a strong acid like hydrogen chloride dissolved in water produces a bunch of H plus and Cl minus. Okay, so we have only these ions present in solution. We have none of the HCl, none of the undissociated HCl present. It's going to break apart completely to give you just these ions. Similarly, your strong bases are going to behave very similar. These will dissociate completely. So like sodium hydroxide, for instance, in water, this will break apart to give you just ions, the only ions present in solution. Okay, you can see a common theme throughout all of these. These strong electrolytes produce only ions in solution. There's none of the original undissociated compound left over. So those are strong electrolytes. So we have the examples that we looked at before, your ionic compounds, but then also things like your strong acids. We looked at hydrochloric acid, but the other strong acids would behave in a similar manner. In contrast to strong electrolytes, we have what are known as weak electrolytes. Okay, and weak electrolytes, in contrast again, is something that does produce ions upon dissolving, but we don't get a lot of ions in solution. Okay, so some, we'll say a very small amount are produced in solution. What actually happens here is the majority or most of the compound, whatever that compound is, remains in its undissociated form. So for example, if you look at a something like a weak acid, such as acetic acid, which is this one here, okay, this will break apart. It will ionize in solution to form some H plus, and we will get the acetate ion, right? Dissolved in water, so we're going to go aqueous. But we don't get a lot of these. We only get a small amount of these ions. So there's some of this present, but the majority of this acetic acid actually remains in the undissociated molecule. The majority is in this form, which is undissociated. Okay, so because you only have small amounts of these, right, this solution will conduct electricity, yes, because there are ions present, but it will conduct electricity very poorly. So as a result, the bulb here doesn't glow very bright. It actually glows very dimly because there are small amounts of ions in solution. And that's because this thing is a weak electrolyte. Okay, the majority of the molecule or the substance exists in its molecular form, unassociated form. Now, one key thing that you want to look at here, if you're presented with equations, is you will see an arrow that looks very different. And the arrow here has a double-headed arrow. It actually doesn't point in the one direction like a normal arrow does. We'll see normal. Instead, what we're going to see is an arrow that goes in one direction with a half head and another arrow that goes in the reverse direction with a head. All right, this tells us that's your clue that whatever we're dealing with here doesn't dissociate completely. Yes, it goes in left to right, but it also goes right to left. So this reaction goes in both directions. Left to right, reactant to product, but also right to left, which is product to reactant. So examples like these, we're going to take a much closer look at these when we get into take General Chemistry 2 later on. But for right now, when you see that double-headed arrow, what that means is that we have two reactions happening simultaneously. We have both a forward and a reverse direction. So forward going left to right, and the reverse going from right to left. And both of these happen at the same rate or the same speed. And we say that we have a system there known as a dynamic chemical equilibrium. A lot of terms that may mean large things, but actually it means very simple things. Equilibrium, or just simply equilibrium. Okay, and what this means is you have both the forward and the reverse reaction happening at the same time at the same speed. So if we go back to our example up here, okay, what's happening is my acetic acid, this thing, is ionizing. It's producing H+, and it's producing the acetate ion. But what is also occurring here is that these two things are now recombining to form back the original undissociated acid. As a result, we don't have a lot of these ions, which makes this a weak electrolyte. So when we have to determine whether something is a strong or weak electrolyte, there are certain steps we can follow. And your book does a good job here of outlining the systematic way to approach that. So if you have a compound, first of all, determine is it ionic or covalent, or ionic and molecular. So we have some examples down here. We have sucrose, fructose, we have sodium citrate, potassium citrate, and we have ascorbic acid. All right, so if we take a look at the first two, both sucrose and fructose, right, these are made up only of non-metals. So these would be covalent, right, or molecular. So because of that, then we can assume that these are going to be non-electrolytes. Okay, these are not made up of ions, and neither are they strong acids, weak acids, strong bases, or weak bases. So let's take a look at the other ones. So it's molecular, right? These are molecular covalent compounds. Is it an acid or a base? Well, neither of these are acids or bases. As a result, they're non-electrolytes. Take a look at the other ones. So let's see, we'll do this in orange. Sodium citrate and potassium citrate, right? We know just based on the fact that these contain metals in them, that these are going to be ionic because of the potassium and the sodium. Okay, so is it ionic or molecular? Well, if it's ionic, we can assume that it's going to be a strong electron. Right, it'll dissociate into its ions completely. And the last one, ascorbic acid, obviously it's in the name. Ascorbic acid, this is acid. Well, is it a strong acid or is it a weak acid? And it's not one of the strong ones, so that means it's going to be a weak acid as a result. It is going to be a weak electrolyte. Okay, so are you going through to determine electrolytic characteristics? You want to follow these steps. They're a good systematic way to determine the nature of your substances.